Hey everyone and welcome. Today, we're going to pull back the curtain on our power grid and talk about one of its most important but kind of unsung heroes, automatic voltage control. Yeah, it's a system that's working around the clock, 24/7, to make sure our lights stay on and all our devices are safe.
So, have you ever really thought about it? What is it that keeps the electricity flowing into your home so incredibly stable? We all just, plug our stuff in and we just expect it to work. But making that happen? Well, that's a massive, nonstop job.
Because here's the thing, here's the fundamental problem. Voltage isn't naturally stable. Not at all. Anytime demand changes, and I'm talking from an entire city waking up in the morning to a single big factory shutting down for the night, it causes these fluctuations. And those waves in the voltage, if nobody's managing them, are a huge threat to the entire system. And yeah, every single thing you have plugged into the wall.
And that gets us right to the heart of the power grid's constant balancing act. See, it's not just about getting power to you, it's about getting the right kind of power. Too much voltage or too little, both can be totally catastrophic. So keeping it steady, well, that's an absolute must.
A good way to think about how important this is to look at its twin, frequency. For most power grids, keeping the frequency rock solid is rule number one. Well, voltage is exactly the same deal. It has to stay within these very specific, very narrow limits. And this isn't just like a friendly suggestion. It's absolutely essential for protecting everything from our sensitive electronics at home to the massive transformers that run the grid itself.
So, how in the world do grid operators deal with this constant flux? It's not like there are thousands of people sitting at dials, right? No way. Instead, they rely on the real hero of our story, the automatic voltage controller. Or, AVC for short. This is the amazing automated system that does all the heavy lifting for us. Okay, so what is it? At its core, an AVC is basically an automated regulator. Its whole job is to watch the voltage coming out of a generator, which, by the way, is often called an alternator in this world, and then controls something called its field excitation. Now, the easiest way to think of field excitation is like a dimmer switch for the generator's internal magnet. By turning that magnetic field up or down, the AVC can get super precise control over the voltage that the generator is putting out.
So how does this thing actually work? Well, it's not just one magic box. It's really a team of key players all working together in perfect sync. Let's kind of peel back the layers and break down the anatomy of the whole system.
We've basically got four main components in this loop. First, you've got the generator, the alternator, which is what's actually making the power. Second is the exciter, and its job is to create that magnetic field the generator needs to even work. Third, we've got the power amplifier, which takes a teeny tiny little control signal and juices it up into something powerful enough to actually make a difference. And last but not least, you have the sensor, and it has one job: constantly measure the voltage coming out.
So how do all these parts play together? The real magic here is that they don't just do their own thing. Instead, they form this continuous, super high-speed feedback loop, making tiny adjustments every single second to keep that voltage exactly where we need it to be.
And the whole thing, the entire process, boils down to this one critical comparison. On one side, you have what's called VREF, or the reference voltage. That's our perfect target. It's the exact voltage we want. Then on the other side, you have VT, the terminal voltage, and that is the actual voltage the sensor's reading in the real world right at this very second.
The real intelligence of the system comes from constantly calculating the difference between those two values. That difference, no matter how ridiculously small it is called the error signal. And that signal, well, that's the whole ballgame. It's the piece of information that tells the system exactly what to do next. Is the voltage a little too high? Is it a tad too low? The error signal has the answer. So you can picture this loop running constantly. First, the sensor compares the target voltage to the actual voltage. That comparison immediately generates an error signal. Then the power amplifier grabs that little signal and boosts it way up. That newly powerful signal is then shot over to the exciter, telling it to either crank up or dial down the generator's magnetic field, and boom, that adjustment instantly corrects the generator's voltage, pushing it back toward the target. And this happens again and again and again, faster than you can even blink.
Now, this brings us to a really fascinating and, honestly, a pretty important reality in the world of engineering. In a system like this, the goal isn't actually perfection, it's stability.
See, the AVC is what's known as a Type 0 control system. And here's the weird but totally true thing about this kind of system. To keep a steady output, it actually needs a small constant error signal to always exist. Think about it like a sailor who's trying to steer a boat directly into the wind. They need that constant pressure of the wheel pushing back on the rudder to know how to steer. If that wind, that error signal, suddenly dropped to zero, they'd lose all their information and wouldn't know which way to turn. So the big takeaway is this. We can't ever have the exact target voltage. It's impossible, because that tiny bit of error is what keeps the whole system steering correctly. But that's totally fine, because what we can get is a voltage that is always, reliably, within those specified safe limits. And for the power grid, that stability is all that really matters.
And that's the end result. It's because of the constant, tireless work of the automatic voltage controller that we all get a stable, reliable power supply. It's this completely invisible system that is literally keeping the lights on and making sure our modern world just keeps on running.
You know, the AVC is just one of literally thousands of these hidden automated systems that are quietly running our world in the background. It really makes you wonder, right? What's another one of those critical systems that we all just completely take for granted every single day? Definitely something to think about. Thanks for joining me.